Okay, now this is a brief video on empirical formula. So what's the purpose of an empirical formula? An empirical formula is an intermediate step in finding the actual molecular formula of a compound. So let's say the compound you're dealing with is C2H4, ethylene. If you do measurements in the lab and weigh the mass of that compound, you first get the empirical formula. The empirical formula is simply the ratio of the carbons to the hydrogens. So if you have C2H4, it means you have 2 carbons for every 4 hydrogens, but like a fraction, you can reduce that down and say that there's 1 carbon for every 2 hydrogens, and that's called the empirical formula. It's not really of any use to us other than using it as an intermediate step to find out what the actual molecular formula is, C2H4. So a molecular formula is the actual formula of a chemical compound. An empirical formula is the smallest whole number ratio of atoms of each element in a molecular formula. So again, CH2 would be the empirical formula of the actual molecular formula for ethylene, which is C2H4. CH2, C2H4. So they're the same ratio of carbons to hydrogens. All right, empirical formula is the formula, a chemical compound that shows the smallest ratio of its elements. So let's do an example. What's the empirical formula for butane? So this is like reducing a fraction. You divide through by 2 to obtain C2H5, and that would be the empirical formula for butane. 2 carbons for every 5 hydrogens, but the actual formula is 4 carbons and 10 hydrogens. There's no actual molecule with the formula C2H5, but this shows the simplest relationship between the number of carbon atoms and hydrogen atoms. Okay, so go ahead and find the empirical formulas for each of these. Well, H2O water, the empirical formula for H2O, think of it as a reduced fraction, 2 hydrogens for every 1 oxygen. You can't reduce it any further than that, so it's H2O. What about N4SE4? Well, you can see that you can factor out or divide through by 4, and that gives you NSE. There's 1 nitrogen for every selenium. What about C2H6? And you could reduce that down to CH3. There's 3 hydrogens for every 1 carbon. Okay, using laboratory techniques, you will learn you can determine the number of grams of product in chemical reactions. Using the grams of products, you can compute the moles and then the empirical formula. So let's take a decomposition reaction. That's one where it breaks apart into from 1 compound into 2 compounds or elements. And a decomposition reaction is one in which compound is broken into its elements. There's an example, N to N, NO to N plus O. By measuring the mass in grams of the N and O we produce, we can determine the empirical formula. So let's take an example. A decomposition reaction produces 1.443 grams of selenium and 5.841 grams of bromine. What is the empirical formula of the SeBr compound that was composed? So here are the steps. First, you compute the number of moles. Anytime you're dealing with a chemical equation or a chemical formula, you have to be in moles. It does not understand grams. Grams is a foreign language to a chemical equation. So we need to have that in moles. So you take the molar mass, you get that straight off of your periodic table. So for selenium, look at your periodic table, find Se, and down at the bottom of that square, you'll see that it's 78.96 grams per mole. So we set up a conversion factor here, 1 mole of Se for every 78.96 grams. Grams of Se cancels with grams of Se, and you end up with 0.018 moles of Se. Same thing for Br. Go to the periodic table, find the molar mass of bromine down at the bottom of the square for bromine, and it's 79.9. So you make a conversion factor. 1 mole of bromine equals 79.90 grams of bromine. So you set that up as a ratio so that the grams of bromine cancels out. And you end up with 0.073 moles of bromine. Now that you have the moles, you make 2 ratios. Create a ratio of the number of moles for each element you obtained. Place the smallest number of moles you computed on the previous slide on the bottom of all. Well, there's only two ratios in this problem, on the bottom of both ratios. So there you go. So for Br, it's 0.073 divided by the number of moles you calculated for selenium, 0.018. And for selenium, it's 0.018 over 0.018. So when you do the math on that, just do simple division on your calculator. Divide the top number by the bottom number. For selenium, it would be 0.018 over 0.018 would be 1. And for bromine, it would be 0.073 over 0.018 would be 4.5 over 1. Okay, so now the next step is you multiply the top and bottom of the fraction by whole numbers, 2, 3, 4, until you have a whole number on the top and on the bottom. Dalton's law, one of Dalton's postulates of atomic theory, was that atoms have to combine in whole number ratios. So 4.05 is really close enough to 4. If it's within 0.05, 0.05 either way, high or low of a whole number, you can approximate that as a whole number. So 4.05 would really round to 4, and the 1 would round to 1. So you don't need to do anything further. You have a 4-to-1 ratio. And so you place these numbers as the subscripts of the elements. So the empirical formula would be SeBr4. Again, the cation, this is an ionic bond. The cation goes in front, the metal, and the nonmetal bromine goes second. So selenium bromide is what this would be. Let's do another. Okay, a decomposition reaction produces 1.651 grams of silver and 0.1225 grams of oxygen. What is the empirical formula of the silver oxide compound that was decomposed? So see if you can remember, it's just 4 steps here. So first thing, you always have to convert to moles when you're dealing with a chemical reaction or chemical equation or chemical compound. So do that conversion. So for silver, you get the 107.87 off your periodic table where you find silver, and you have 1.651 grams. So you do the conversion, grams of silver cancels out, you end up with moles of silver is 0.0153. Same for oxygen. The molar mass of an oxygen atom is 16. So to do the same division, you get 0.0077 moles of oxygen. Okay, what do you do next? See if you remember. Well, now you make those 2 ratios. So create a ratio of the number of moles for each element you obtained. Place the smallest number of moles you computed on the bottom. Again, it's only 2 compounds here. Okay, so there's silver. It's 0.0153 over 0.0077. And for oxygen, it's 0.0077 over 0.0077. You're always going to end up with one of the elements having its own number of moles over itself. So that's always going to be 1. All right. So, place the 1 at the bottom. You don't really have to do that. You have 1 point, you can do that. You have 1.98 over 1. That's what that ratio is. Now, 1.98 is close enough to 2 to call it 2. And for oxygen, you have 1 over 1. So now you multiply the top and bottom of the fraction by a whole number until both of the numbers are whole numbers. So 1.98 we said is approximately 2. So you have 2 over 1. So you don't need to go any farther than that. You really didn't need to multiply by anything. You have a ratio. So you have 2 silver for every 1 oxygen. So place these numbers as subscripts of the elements. And this is the empirical formula. And it's Ag2O. All right, one more example here, and this time we're also going to figure out the actual molecular formula, not just the empirical, but the molecular formula. So watch this one because it's a little different. So a combustion of an unknown hydrocarbon. Hydrocarbon always means a CH compound of some sort. So there you see the numbers of grams that it produces. So hydrocarbon is a compound made of carbon and hydrogen. The combustion reaction burns a hydrocarbon and has the general formula of CXHY, so you don't know what those subscripts are. That's what we're trying to find out. O2, burned with O2, combusted with oxygen, gives you carbon dioxide and water. Okay, so here is how we do this calculation. We know we're starting off with 33.01 grams of CO2. So we're going to start off over on the left side of our equation with that number. We need to get moles. What we're going for is how many moles of carbon do we have? So we need to get from grams of CO2 to moles of carbon. So we know that for carbon dioxide, there's 1 mole of CO2 for every 44.01 grams of CO2. So that's our first conversion. So now we've canceled grams of CO2, and we now have moles of CO2. But we're not interested in moles of CO2, we're interested in moles of carbon. So what we look at here is we see that when we do our calculation, we have 0.75 moles of CO2. That's 33.01 divided by 44.01. So you have 0.75 moles of CO2. But again, we're not interested in CO2, we're interested in carbon. So we know that we can see that we have 1 mole of carbon for every 1 mole of CO2. You see there's 1 carbon atom in 1 CO2 molecule, so it's a 1-to-1 relationship. So 1 mole of carbon for every 1 mole of CO2. So now moles of CO2 are going to cancel, and you end up with just moles of carbon as your final calculation. And there it is. That's the number that shows up under CO2. But now we have not moles of CO2, but moles of carbon. So the reasoning goes like this. All the carbon that's in the carbon dioxide had to come from that CH compound over on the left. There's no place else it could have come from. So if we know we have 0.75 moles of carbon in CO2, we must have 0.75 moles of carbon in that CH compound over on the left side of the equation. So we now know the moles of C in the hydrocarbon compound. Okay, now we've got to figure out hydrogen. How many moles of hydrogen do we have? So we say we have 13.51 grams of H2O. So we're going to start our equation with that. Then we're going to take the molar mass of H2O, which is 18.02. Again, 16 for the oxygen and 1.01 for each hydrogen. So that's 2 times 1.01 plus 16 is 18.02. So that tells us how many moles of water we have. And we have 0.75 moles of water. But we're not interested in moles of water, we're interested in moles of hydrogen. So what do you see in that equation? You see that there's 2 moles of hydrogen, there's 2 hydrogen atoms for every 1 water molecule. So it's a 2-to-1 relationship. So for every 2 moles of hydrogen, there's 1 mole of water. Or this said the other way around, for every 1 mole of water, you have 2 moles of hydrogen. So now we can run that equation through and we end up with 1.5 moles, should be moles, of hydrogen. So we have 0.75 moles of carbon, 1.5 moles of hydrogen. So now we can place that as the subscript for our CH, our hydrocarbon there. 1.5 moles of hydrogen over 0.75 moles of carbon. That's a 2-to-1 relationship. So the empirical formula is C1H2. The 2 belongs to the hydrogen, the 1 belongs to the carbon. So that's the empirical formula. But what's the actual molecular formula? Well, to do that, you have to know one more piece of information. So continuing the last problem, if in a lab experiment you calculate 1 mole of the gas has a mass of 28.06, what is the molecular formula? And the molecular formula is the actual formula of the compound. How did you know that it was 28? How could you tell that? Well, we learned a principle that at standard temperature pressure, that's 0 degrees centigrade and 1 atmosphere of pressure, that any gas, doesn't matter what the gas is, will have a volume, 1 mole of any gas will have a volume of 22.4 liters. So let's say you got yourself a 22.4 liter container and you pumped it was a vacuum, so it had no pressure inside, and then you start pumping it full of this gas, whatever this gas is, until you get the pressure up to 1 atmosphere. And then let's say you can set the temperature inside that container, and so that it's 0 degrees centigrade. So now you have the conditions of standard temperature pressure, 0 degrees centigrade, 1 atmosphere, and you also have a container that's 22.4 liters. Therefore, you know that you have exactly 1 mole of gas inside that container. Now that gas is floating around inside. If you then lowered the temperature of that container, you sealed it off and then lowered the temperature so that that gas all condensed down into a liquid and maybe even into a solid that settled on the bottom of the container, you could then take the container and put it up on a scale, weigh it, subtract the mass of the container, and you'll know what the mass of that substance is inside. So that's kind of just a thought experiment of how you could figure out what the molar mass is. So you figured that out, that it's 28.6. So what's the molecular formula? So we had a formula that we need a conversion or a multiplication factor, and that's simply the molar mass divided by the empirical mass. So the molar mass, we just said, is 28.06. The empirical mass is the mass of the empirical formula CH2. So C is 12.01. Get that off your periodic table. H is 1.01 plus 1.01 because there's 2 hydrogens. That gives you 14.03. So if you divide 28.06 by 14.03, you actually get exactly 2. So what you then do is take your empirical formula CH2 and multiply the subscripts by 2, because that's the factor you just calculated. And so your actual molecular formula is C2H4. So you need to know that last piece of information, what the molar mass of the substance is. So anyway, that's how you do empirical formula problems.